Weak acids. Weak acids are those that do not dissociate very much. So if we take a weak acid, such as nitrous acid, it does form some hydrogen ions and some nitrite ions, but there's not many ions, so its Ka value is very small. So all weak acids dissociate to a small extent. Hypochlorous acid is one of our weak acids, HOCl. Notice the O is the oxygen, and the hydrogen is attached to the oxygen, just like we saw with strong acids. When this acid dissociates, it forms hydrogen ions and hypochlorite ions. ClO1- is the way I would like to write it. If you think about its equilibrium expression, its Ka would be hydrogen ions times the concentration of the hypochlorite ions over the unionized molecule. And this ratio would be very small because most of the molecule in the acid would be HOCl. Okay, phosphoric acid is H3PO4. We call it a triprotic acid because it has 3 protons on it. When it dissociates, the first step of dissociation is one hydrogen comes off and we form H2PO4 with a 1- charge. In a complete ionization, you would lose the H2, would lose 1 hydrogen, and then you could completely ionize by losing all 3 hydrogens. Again, a weak acid. All right, carboxyl group is the organic acids. What you're looking for is the COOH. R or X is like the rest of the molecule. The one that we will use most often is acetic acid. You see it written as such here. That's the same as CH3, COOH, so you can recognize that ending. What it looks like structurally is you have your carbon with 3 hydrogens around it. There's your C, double bonded to your O, an O, and an H. The ionizable hydrogen is the one that's on the oxygen atom. So the ionizable hydrogen is this guy right there. If you want to pick it out here, there's the acidic hydrogen. When it ionizes, well, first of all, we often write acetic acid, HC2, H3O. So that's hydrogen acetate. This makes it easy to see that front hydrogen come off, and then you're left with the rest of the ion. C2H3O, 1-, the acetate ion. A weak acid, not much ionization. Benzoic acid looks complicated, but if you just check out that last hydrogen, that's the ionizable hydrogen. That's the one that would come off when it ionizes. Here's some of our values for Ka. The smallest values are at the bottom. There's your ammonium ion, and there's that bisulfate ion. A term that I mentioned the other day was amphoteric substances. Amphoteric is something that will act as an acid or a base. If we take a water molecule, it will ionize with itself and form hydronium ions and hydroxide ions. So this is just liquid water. Liquid water forms your ions. If we want to write it with just hydrogen, just start with your H2O It's in equilibrium with hydrogen ions and hydroxide ions. So amphoteric just means it can act as an acid and as a base. So water is the ion product constant for water. It is dependent upon temperature, like all our equilibrium constants. And the one that's measured at 25 degrees C has a specific value. Now, this equation is on your AP sheet, and so you might want to pull that out and give it a look. If you think again about H2O dissociated, you form hydrogen ions and hydroxide ions. And it's a one-to-one relationship. So if you have 1 mole of water, you're going to get 1 mole of hydrogen and 1 mole of hydroxide. So the hydrogen and the hydroxide are always the same. And when measured at 25 degrees Celsius, each has a value of 1 times 10 to the minus 7th molar. So if you multiply those two numbers together, you get Kw to equal 1 times 10 to the minus 14. That is always true when we have water. So always. And this is true at 25 degrees Celsius. So a neutral solution will have hydrogen equal to your hydroxide. Whoops, that last one was an acidic solution, has hydrogen greater than hydroxide, and your basic solution has your hydroxide, its concentration is bigger than your hydrogen. So these come from our textbook, Zumdahl 9th edition. We're going to calculate concentrations of hydrogen and hydroxide. So our first one, we have 1 times 10 to the minus 5th molar hydroxide. What we're looking at is Kw is equal to hydrogen times hydroxide. This is all happening at 25 degrees Celsius, so we know what Kw is. It is 1.0 times 10 to the minus 14. This is on your AP sheet. And just verifying, and it does have the temperature listed by it. So to find this one, there's our hydroxide, that's our concentration. We're trying to find the hydrogen, so if we just rearrange our equation, we have concentration of hydrogen is equal to Kw divided by our concentration of hydroxide. So putting our numbers in, 1.0 times 10 to the minus 14 divided by 1 times 10 to the minus 5th. Before you pull out your calculator, just think about it. You can do it. Remember, you subtract exponents. So negative 14 minus 5 gives you 1.0 times 10 to the minus 9th. And now we're expressing it, so I'm going to put my unit in for molarity. Put a box around it. Our next one. This time, if we have 1 times 10 to the minus 7th molar hydrogen, we're trying to find our hydroxide. And we're using the same equation. Kw is equal to your hydrogen multiplied by your hydroxide concentration. And I'm taking a really long route to find something that you might see as quite obvious. If the hydrogen is 1 times 10 to the minus 7th, we know that the water is the same. So, excuse me, I said the wrong thing. The hydroxide is the same. 1.0 times 10 to the minus 7th molar for your hydroxide concentration. So you could go straight there if you saw that. If you have a very concentrated acid, you're still going to have Kw is equal to your hydrogen concentration times your hydroxide. So thinking about that, it's going to be a very small number. So we have hydroxide equals Kw over your hydrogen, and 1 times 10 to the minus 14th divided by 10 molar will give us a value of 1 times 10 to the minus 15th molar for your hydroxide concentration. So now look at the temperature given for our last practice problem. It's at 60 degrees, so our Kw is dependent upon the temp. So this problem has it at 1 times 10 to the minus 13th. We're using Le Chatelier's principle to predict whether the reaction is exothermic or endothermic. So we know that at 25 degrees, it's 1 times 10 to the 14th. So if this number is bigger, you want to think about, are more products formed, or did it shift to the left for more reactants? So 1 times 10 to the minus 13th is bigger than 1 times 10 to the 14th. So we know that this process is endothermic, and by adding energy, I shouldn't have written endo there, but energy there. How about that? Energy, it's going to shift to the right, creating more ions, which will make a greater Kw value. Our last one is to figure out what hydrogen and hydroxide concentrations are when it's at this 60 degrees Celsius. So we're just going to take our Kw, and we know that it's the concentration of hydrogen times the concentration of oxygen. They have to be the same. So I'm going to use X for my concentration. And I'm going to take the square root of 1.3, oops, excuse me, how about 1 times 10 to the minus 13th, right? It's like Kw is equal to X squared, and our X is equal to 3 times 10 to the minus 7, there we go, molar, and that is our concentration of hydroxide as well as hydrogen. Those are all equal to our calculated molarity.